Let's solve this abstract algebra question. I love this because it ties together lots of concepts that you would learn in a first course on group theory. So you have a group G, and you have some homomorphism from G onto this other group here, and you're given that it's surjective, and that the kernel, whatever that is, of that homomorphism has 5 elements. And then you're asked to show that G has a bunch of normal subgroups of all these different sizes. So where do we begin? And we're going to use 2 key ideas that you would learn in a class. One is that normal subgroups are exactly the same as those that arise as kernels of a homomorphism. So since we have a kernel upstairs, that's going to be helpful. And then secondly, we're going to use something called the first isomorphism theorem, which tells us that whenever we have a surjective homomorphism, there's actually an equivalent or an isomorphism between the group on the right and something called a quotient group. So let's see how these are used. Okay, we've got this surjective homomorphism phi, and if we use this first isomorphism theorem, then it's going to say that Z6 cross Z2 is going to be isomorphic to G modulo the kernel of that. Now if we think about the size of these 2 groups, this group over here has order 12, right? It's just going to be the product of 2 and 6. Now on the right-hand side, we're given that the kernel has order 5, and so for everything to work out, the order of G would have had to be 60 to begin with. And so we can conclude that the order of G has to be 60, right? So now let's look and see what sort of data we have. So I've added in that information we now know about our group. And one thing that's true is that any group is always a normal subgroup of itself. And so that's where we're going to get 60. That would be the subgroup G itself. The identity subgroup just itself is always normal, and that has 1 element. So that's going to give us a subgroup of order 1. And we know the kernel, in that fact that we talked about, the kernel is always going to be normal. So there's our subgroup that's normal of order 5. How are we going to get all these other ones? This is actually where the fun begins. If I start with this surjective map phi, and then I just keep going, and I project, say, onto that first factor, right? That's just sending everything over here to the identity. Well, what's going to happen is now, if I compose those 2 maps, I'm going to have another surjective map, but this time from a group of order 60 down to a group of order 6. And so if I call this map, I don't know, psi, then what's going to be true is that the kernel of psi is going to have order 60 divided by 6, which is 10. And so if we wanted a normal subgroup of size 10, we could just work out what this map is, and the kernel of it would have exactly 10 elements. That's how we got that element there, and now maybe you can see how the rest of this proof is going to go. If we look back at what we had up here, this group Z6 is actually isomorphic to Z3 cross Z2. And so really, we can think of this as having 3 different factors. And once we have that, we can actually write down maps not just to Z6, but also to Z2, to Z3, and even to things like Z2 cross Z2. And so if we think about the orders of all of these groups, they have orders 6, 2, 3, and 4. And then when we do the same thing that we did upstairs, when we divide those into 60, the kernels of all of these compositions are going to be exactly the things that we needed. I thought this was a really fun problem. What should we do next?